We'll now begin our discussion of section 6.5, where we will define the inverse trigonometric functions. We're going to begin by looking at the graph of our sine function. We want to review several topics from algebra before we begin. First of all, remember that in order for a graph to be a function, it must pass the vertical line test. And so our sine function does pass the vertical line test. Remember that the vertical line test means that you can draw a vertical line and it only passes through the graph in one place. So if I were to draw my vertical line here, I only hit the graph in one place. If I were to draw it here, I only hit the graph in one place, and so forth. Now, also in an algebra class, we talk about a specific type of function known as a one-to-one function. In order for a function to be what we refer to as a one-to-one function, that function must pass the horizontal line test. And as you can see, the sine function does not pass the horizontal line test. If I draw a horizontal line here, I have crossed the graph in more than one place. And so while the sine graph is a function, it is not a one-to-one function. Now, if you recall, the reason that we are concerned if a graph is a one-to-one function or not is that a graph must be one-to-one in order to have an inverse. If a graph is not one-to-one, then it does not have an inverse. And so the problem is that we've now concluded that the sine function is not a one-to-one function. Therefore, it should not have an inverse. However, the section that we're going to look at does talk about the sine function having an inverse. And so we have to figure out a way to make that make sense in our head. At some point, mathematicians have decided that while the entire sine function may not be one-to-one, if you could restrict the domain, then you might have a piece of the sine function that would meet the criteria of being one-to-one and would therefore have an inverse. Now, there are lots of different ways that the domain could be restricted to make this work. But the accepted way is to drop a line at negative pi over 2 and another line at pi over 2. And to say that when we define the inverse sine function, we are only going to define it on this piece of the graph. So in other words, we're going to ignore everything that does not fall inside the blue dotted lines. So if I am looking solely at this part of the graph, does it meet the criteria of being a one-to-one function? And we would say yes, that part is a one-to-one function. And therefore, if we restrict the domain in that manner, we can go ahead and define the inverse sine function. Okay, so let's talk notation for just a second. When we talk about an inverse sine function, we can use one of two notations. So we can say that our y is equal to sine x is equivalent to x equals arc sine of y. And arc sine is a way of referring to an inverse. So that is one notation that we can use to reflect the inverse sine function. We can call it the arc sine. The other notation that you will commonly see for our sine function is x is equal to sine with a -1, kind of like an exponent, of y. And this is the notation that our book uses for inverse sine. And the reason that they choose that is because that is most closely linked to what we learn in the algebra portion of the course, where we are dealing with a function f. And when we talk about its inverse, we're using this notation f -1 of x. And so just for consistency's sake, we're going to use that second notation for our sine function, or for the inverse of that sine function. All right, so once we have the notation down, the other thing that you have to keep in mind is that it is only defined from -π/2 to +π/2. All right, so let's go ahead and look at the formal definition given to us in the book. It says that arc sine of y is the angle whose sine is y. We're going to look at that in just a minute when we work some problems. The restricted domain of the sine function, here's the restriction that we talked about on the previous slide, and the range is -1 to 1. Okay, we did not look at the range, so let's go back and take a quick look. If we restrict on the domain from -π/2 to +π/2, the highest point inside that restriction is at 1, and the lowest point inside that restriction is at -1. So our graph, the piece of the graph that we're looking at, would have a range value window from -1 to +1. All right, and then it goes on and says the domain of arc sine is -1 to 1, and the range is -π/2 to +π/2. Remember that when we go from a function to its inverse, the domain and the range switch places. The x and the y values switch from a function to its inverse. So that is why we're seeing the domain of the original function being -π/2 to pi, and that becoming the range of the inverse. And the same would apply for the -1 to 1. When we get through these functions, we're going to summarize at the end, so we'll have the basic pieces of information that we need in order to work the problems. Okay, so let's go ahead and look at our cosine graph, and let's define an inverse cosine. All right, so this is a picture of our cosine graph. So this is y is equal to cosine x. Again, it does pass the vertical line test, but it does not pass the horizontal line test. And so we need to restrict the domain. We cannot restrict the domain in the same way that we did with the sine. If we restrict our domain from -π/2 to +π/2 like we did before, we still don't pass the horizontal line test. And so we have to restrict in a different way than what we did for the sine graph. So the accepted restriction on the cosine is that we're going to restrict from 0 to pi. And we're only going to consider the piece of the graph that lies in between these two lines. If we only consider that piece of the graph, then it does pass the horizontal line test, so it is 1 to 1, and the inverse function would be defined. Okay, so again, we're going to have as our notation x is equal to cosine inverse of y, and the restriction will be between 0, and pi for the cosine. The range values would still fall from -1 to +1, just like they did on the sine. Now, one thing that they're going to ask you to do in the early portion of the homework is to graph one of these inverse trig functions. So I want to show you that on this cosine because I want you to see that what is happening is, again, the x's and the y's are switching places. So I'm going to go ahead and grab a couple of these points off of this cosine graph. For example, this point here, which is the point pi -1. This point here, which is the point pi/2, 0. And maybe this point, which is the point 0, 1. And remember that these are points on the original cosine graph. When we move to the inverse, these points should have a switch between the x and y coordinates. So on the inverse graph that we're about to look at, we should have the point 1, 0 instead of 0, 1. We should have the point 0, pi/2 instead of pi/2, 0. And we should have the point -1 pi instead of pi -1. So we could easily plot those points and sketch the graph, and that is done here. All right, so we can see that we have our 3 points that we noted. We have the point 1, 0 marked on our graph. That's here. We have the point 0, pi/2. Which is actually, they have it mislabeled here. This is this point right here. And this is the point 1, 0. All right, and our third point would be -1 pi. So we go -1 up to pi, and there's the third point that we noted. And so we could plot those 3 points and then connect the dots to make a graph for our inverse cosine function. All right, and finally, let's look at the tangent. So we have a graph of our tangent function, and we want to look at what our inverse tangent function is going to look like. So we're talking about x is equal to inverse tan of y. And let's think about the restriction. Again, we have to restrict the domain because if we don't, then when we do our horizontal line test, we will cross the graph in more than one place. And so when we restrict, we can restrict in the same way that we did with the sine. We're trying to keep things as consistent as possible. And so restricting from -pi/2 to +pi/2 would work if we only considered what is in between. Now, note that if we restricted from 0 to pi, like we did on the cosine function, that would also work, but it would produce a graph that's split into 2 pieces, and an entire continuous graph like we have here is always going to be preferable over a graph that has 1 piece here and 1 piece here. And so that is why we use the -pi/2 to +pi/2 restriction on the domain when we do the inverse tangent. Now on our next screen, they have summarized these 3 graphs for us, and we're going to do that in just a second, but you can go ahead and take a look at that and see that this is what we do have. We have the same restrictions for the sine and the tangent as far as where we are going to pull from. We can see our different notations. But again, we're going to summarize this in just a second. All right, so let's go ahead now. We've talked through the sine, the cosine, and the tangent for the inverses. We are not going to look specifically at the graphs for the other 3 functions, but I am going to write them in our chart here for our reference. All right, so we're going to begin with what we already know, which would be our inverse sine. So that's going to be x is equal to sine inverse of y. And we said the restriction was from negative pi over 2 to positive pi over 2. And then I have a column for quadrants. When we work problems in our next presentation, the answers are going to come from certain quadrants. And so we want to think about what quadrants are allowed with our restriction. So if you think about your graph, we know that leaving the positive x-axis and heading this way, we'll reach pi over 2. Leaving our positive x-axis and heading this way, we'll reach negative pi over 2. And so our restriction on our inverse sine says we have to stay in either a quadrant 1 or a quadrant 4. This is 1, 2, 3, 4 as we count around. So I'm going to go ahead and in this spot put quadrant 1 or quadrant 4. Now for our cosine function, we'll have x is equal to cosine inverse of y. And we said the restriction would go from 0 to pi. And in terms of quadrants, 0 to pi would indicate either quadrant 1 or quadrant 2. We know that this is our pi value over here. For our tangent inverse function, our restriction goes from negative pi over 2 to pi over 2. And note the parentheses that I'm using here because we know that the tangent function is not actually defined at pi over 2 or at negative pi over 2 because we have asymptotes on the graph. Okay, it does not change the quadrants, so we'll use the same quadrants that we used for the sine, so either 1 or 4. Now, in terms of our other three trig functions, we want to pair these up with the functions that we already have. So when I go to look at my cosecant, we know that cosecant and sine go together because they're reciprocals. And so they are going to have the same restrictions and the same quadrants. So we have for the restriction on the cosecant, negative pi over 2 to pi over 2. And again, that will be quadrant 1 and quadrant 4. Similarly, when we go to our secant inverse function, remember that secant and cosine line up. And so our inverse secant function will have the same restriction and the same quadrants as the inverse cotangent. So 0 to pi and quadrant 1 or quadrant 2. And then we move to our last one. And we know that in math there are always exceptions. And the cotangent is an exception because it does not do the same thing that tangent does. It actually does the same restriction that cosine and secant do. And you can look at the graph and see why you have to have that restriction set from 0 to pi. All right, and that's going to be quadrants 1 and 2. And actually, just like with our tangent, we're going to need to make that a parenthesis because we're going to have asymptotes at 0 and pi. So now we have defined all 6 of the trig functions. We know how to restrict the domain for each one, and we know which quadrants that restriction of the domain is going to include on our graph.